Okay, so I actually have a live coding experience and no slides at all. I'll post now the GitHub repository that I will use during this talk. It should be in the chat. And let me open the screen share. Okay, so first of all, I'd like to thank DM because her introduction actually saved most of my introduction part. I'm going to speak today about an effect system for TypeScript that I've been developing during the last 6 to 8 months. It's heavily inspired by Zio, and in particular by the usage that Zio makes of the environment. Something on the chat. Sorry, I can't see the chat.
Have you got the chat okay?
Yeah, I think so. Anyway, yeah, I'll ignore the chat for now.
Okay. I think they're asking, are you able to increase the font size, zoom in on your screen a bit at all? Is that
my font size, can everybody see now? Oh, that's a bit too much. Is it fine now?
Is that better, guys? Yeah, I think that's fine. Thank you, Michael.
Okay, perfect. So I was saying it's heavily inspired by Zio and the usage of the environment that Zio make. And I will skip the introductory part about the 3 parameters because we already had that in the previous talk. The only difference in the type parameters is I've added a 4th type parameter to also encode the type of the operation. So Matechs-Effect is able to detect if an operation is synchronous or asynchronous, because in TypeScript, given we target JavaScript environments, we are not able to block any thread. So in case we want synchronous APIs, we can only restrict to synchronous computations. And to make it type safe, we had to encode it in a separate type parameter. So the effect type in Matechs is 4 parameters, S for asynchronous or synchronous. They are encoded as unknown and never representing synchronous operation, unknown representing asynchronous operation. That is a trick in TypeScript because when we mix those in an OR condition, we will always get the unknown winning. So a computation that will be both synchronous and asynchronous will appear as asynchronous. The environment works precisely in the same way as the Zio environment works. There is a special encoding that we are making to be able to encode multiple environments in the same parameter. And basically the environment is always represented as a key value map of a unique resource identifier to a particular service. We're going to see that in details later. The error channel is the same as in Zio. It is contravariant. So if you have an operation that can fail for one reason or another, your type will encode one reason or the other. And at the end, the output type is the same. It's the value. Just a bit of introduction for TypeScript function composition. In Scala, you have by default in the type in the language itself things like and then or similar. In TypeScript, we don't. So there are a few utilities that we've built, actually, that we've borrowed from FPTS to be able to compose multiple functions smoothly. One of those is flow. Flow is the classical function composition. So you can see we have 2 functions, and additional multiplication. We want to add 5 and multiply by 10. We can say that add 5 and multiply by 10 is a function, as a flow of functions, and these will automatically be a function from X to the number that is the result. There is another.
Sorry, Michael, are you able to zoom in your font a little bit more? I think a few people are just having trouble with reading it, just a little bit more if that's possible.
My microphone?
Oh, no, sorry, your font. Yeah, your font.
The font. Perfect. Okay.
Thank you. Sorry.
You're welcome. Another utility, very important one, is pipe. It's just like flow, but it's data first. What does it mean, data first? In flow, automatically we have the type inferred from the first one. In this case, we specify, it's is written with flow. We basically specify the argument at the beginning. Why this is important? Because unfortunately, TypeScript inference works left to right. So whenever we want to enforce some inference from the left parameter, in this case from the result, from the argument of the computation, we have to put it at first. In this way, pipe will effectively work out the full inference correctly. This is, of course, not important to compose additional multiplication, but when we start to compose complex effects with very different type parameters, it works really well. The same two functions written in a way that they use the effect system. They are synchronous computation, so we can use the combinator sync and simply rewrite those two as before. How do we compose? We can still use flow. This time, it's going to be a monadic composition, so we cannot directly stitch the output of one in the input of the other. We are going to have to use chain. Chain is flat map plus map. Actually, it's just flat map. Sorry. It's flatten plus map, so it's flat map. And the chain operation will basically take the result of this and put it in the input of the second one, and the result will be a chain of the two. You can see here we have the 4 type parameters. This means this computation is a synchronous computation. First parameter is never, doesn't require any specific environment. The environment is unknown, cannot fail, has never a failed result, and in case of success, so always in this case, it'll answer with a value of type number. There are type aliases to shorten the things, so we can write the same function using an alias specifying that this is t.sync. You can see the type parameter is transparent, but in this case we have a more clear and compact signature. How do we handle different error types? Let's add a division operation that might fail if we are trying to divide stupidly by 0. This is a way of encoding things in TypeScript to have discrimination over algebraic data types. A smart way is to do tagged objects. So your final composition of A and or B or C or D will be indexed by the tag. It's very important to use read-only parameters because in this case the type will be nominal, and we can see this is a very simple description of an error that says you've divided by 0. Let's write a division function. Takes y, takes x, checks purely if y is 0. In case it's 0, it raises an error, division by 0. Otherwise, it returns a successful operation. The type of this, you can see, is properly inferred. Let's add another operation that can fail. Those operations have really no specific meaning if not for the purpose of taking a look at how the types mix. We are going to see a slightly more advanced examples in the further examples. I'm not sure I'm going to cover everything because it's, I think, slightly too much for 30 minutes, but the repository is open, and after the talk, I'm willing to answer anything. So let's add the second operation. It's a percentage that give an error if the discriminator is out of bounds. So as before, we check, we raise an error, nothing very specific. But we see now the first time we compose 2 different operations. So we want to say that our program takes x and y, takes z, then divides z by x and calculate the percentage over y. Our program is, the type of our program is now, apart from the functions, from the function input, you can see that the return value has properly mixed the 2 error channels. I might have to say that in a normal scenario, TypeScript doesn't have variants. So all of this is done through manual stitching of the various parameters together. And it works very well if you're using TypeScript with a strict flag on. If you don't use TypeScript with a strict flag on, none of this will work fine, because then your function types will not be, basically the type system will be completely unsound. So it's very important to use strict type system. In this case, we saw that the types have mixed properly. We have computation that might fail for a division by 0 or for an out-of-bound error. And let's see how we can handle, for example, the case where we have this division by 0. If we want to handle a single case, we can, and we have tagged errors, we can use this nice handle parameter that will automatically infer everything. So I can say I want to handle over the tag, I want to handle the division by 0, and I want to return purely a 0. And in this case, the type in the output can only fail for an out-of-bound reason. We have, of course, a way to catch all of the possible error types with chain error, and the parameter here, you'll see it's inferred. In this case, it's an out-of-bound. As in Zio, we might have multiple error causes because we might run things in parallel. We have slightly different encoding on the cause. We don't do the both cause, but we have a root cause and an array of remaining causes that is represented as an option of an empty array. So in case you have a second parameter and this is not none, then something else went wrong. There are also the additional die cause that is encoded as an abortion. It's called abort. And there is also the interruption. If you want to catch all, you can use fold exit, and you see you have the full cause as the failure scenario. So to run this, it's a synchronous computation, so we can run it synchronously or we can run it asynchronously. Synchronous operations can run both synchronously and asynchronously, while a synchronous operation can only run asynchronously. It requires no environment, so we can directly run our program. Let's build it. And let's run it to see that it actually works. See, the first result was the program. We passed a 0, so this is a division by 0. The full exit cause will be erased, error, and the error will be a division by 0 with all the message, and there are no remaining errors. The second result, it's handled. We've handled the case of division by 0 by returning a 0. And we have, as expected, the third one, it fails because this is out of bound. So we see that it's out of bound with the proper message. And the 4 handle everything. So the same 150 is again handled to 0. And finally, the 5th result actually succeeds because it had no errors. But this shows, mostly shows in the console the exit states. So let's switch to the actual interesting part. How do we manage environment? First of all, why environment is important. The most important feature of the environment is testability. When we use environment to encode our services, we basically lift our implementations to an environment, to a context that is passed from the entry point of your program. So this makes, well, it's very easy then to develop against interfaces rather than developing against concrete implementations. Anytime we develop against an interface and we are able to swap at runtime the actual implementation, we can have one implementation for test, one implementation for live, or even in some cases, multiple different implementations of live in the same service. For example, in the standard library, we have a logger with two different implementations. The first one is classic console logging. The second one is using Winston. That is a more complex logging system that allows you, for example, to post the logs to an external channel. You can use Kafka or whatever you want. But it's completely, you can develop against a normal logging, and just at runtime you decide, okay, I'm going to use one or the other. They're completely interchangeable. How do we specify environments? We saw in the first step, we encode those as a map. This is a very similar encoding that is used behind the scenes in ZLayer. The ZLayer builds up a map of key values where each environment has a single key and is identified. In TypeScript, we do this manually, and we encode multiple environments with intersection types. So we define first a unique resource identifier. For example, we are building a console service with two functions, a log function and an error function. We declare an interface indexed over the URI, and this is simply specifying the types, the signatures of the function that we want to expose. Then we have the service API. This accesses the log functions from environment and use it concretely. So the signature of these will be, you can see in the right side that this function now requires, it returns an effect that requires a console to be provided to be able to run. The same for error, and now we can use those two functions arbitrarily in our programs, and when we run our programs, we will be required to provide those environments. We can provide a live implementation of the console, where we simply use the underlying console, or we can provide a test implementation, where in the test implementation, we want, for example, to take a references for an array of messages, and we want to, instead of outputting something to the console, we want to keep track of every message that have been sent to our console. We have our program. Our program we use, for example, this is sequence T. T stands for tuple. It means it's like a generalized zip. It means run these, run these, run these, and run these sequentially. So you can say log hello, log error, log something else, error something else, and we can see that our program will now require a console to run. Let's see how we run it in live. We take the program, we provide the console, and we run. If we forget to provide the console, we're going to have a type error. And in the type error, you're going to see that it basically says it requires a console, and the console URI is missing. So you have to provide a console to run. There is no way you can forget a dependency. Let's run this. And we see that it works fine. We're now going to see the test implementation. How does it look in tests? In tests, we have a similar implementation of ZeoTest. You're going to have an in-depth look at ZeoTest later on. But fundamentally, we have two tests. One that assert that our programs correctly interacts with the console log, with the logger environment, with the console environment, and the second test that will check that the live provider actually calls the console. This is a very good way to test things because there is a complete separation of concerns. You test your program against mocked or faked implementations, and you test your concrete implementations of the environment against, in this case, the external world, the console. But the things you have to assert over the console are much less. And especially you don't have to monkey patch a lot of things. Because monkey patching is kind of bad. Doesn't give you fine granular control. Over the syntax, we have a simulation of Haskell's do, or that in Scala it's called for. This simply means construct a reference, an array of test messages, run the program with the test console using this specific reference. After the program runs, take the messages out, then check the messages, the length of the messages, and each single message. Test the console. In this case, we have to mock against the external world. So we do a little bit of monkey patching. Any of the spies that are acquired are going to be automatically released when the test runs. We mangle the things together in a suite. You see, this properly requires, it's a specification of a console. It means you're gonna have to provide a console to run this. Why do you have to provide a console to run this? Because in the second function, we have not provided anything, while in the first we have provided the actual implementation. So this is hierarchical. In the first one, we're gonna use the nearest. In the second one, we have provided nothing, so it's lifted to be provided at the top. Here, of course, during your test, you could require 150 different environments, and they will be properly meshed together. We cannot over-provide things. And if we forget to provide, we have a type error, as in the normal one. Let's run this test. Also, getting the coverage out. And see that the first suite has run, and we have 100% coverage. It means we effectively covered any case. We can take a look at the coverage, how it looks. We use Istanbul to do that. And we're going to see that everything is properly called and properly covered. This is probably better looking. Let's go on point 2. What if we want to mix multiple environments? Before we had a simple console. Now we add a very dumb calculator that only has a single operation, addition. Same as before, service description, service API, live implementation. And this program, you see that will now require both a console to be provided and a calculator to be provided. This is inferred from the usage of log and from the usage of add. Chain tap is like chain, but doesn't change the result. So it's like when you want to log things and not change the output, you can tap with a chain tap. How do we run this? As before, take the program, pipe the live calculator, pipe the live console, and do a run. Here, again, if we forget to provide one, it'll say you haven't provided. If we forget to provide the other, it's gonna say you have to provide the calculator. Let's run this. For the sake of it, result 15 works properly. And let's take a look at this in the tests. As before, here we are mocking the test console, and we are getting our result from the console output. And in a second test, we are actually taking a look at, we are patching the calculator result to check that we are actually calling the calculator with parameters in the proper order. This addition is commutative, you can call it X and Y or swap it. How do we do that? We do it through provide M. Provide M is an extension of provide that is monadically. So you can use an effect to provide to another effect. It means basically we can provide by accessing something from the environment. In this case, we are accessing the same service and we're just patching the implementation and calling the actual implementation after. As before, we get the reference out, take the various calls, and we see that effectively, okay, it was called X, 5, Y, 10. This is very important because many times your services will depend on other services. When something depends on something else, you want to provide monadically and access the other service in your provide function. Same logic, we have a calculator to be provided because somewhere else we are, in both services, we are never providing the calculator. So merging those two will still require a calculator, a live calculator to be provided. We saw it from the coverage as before. Now, this is the unsafe function, the one that runs. It's everything covered, and using this way of developing programs is very, very easy to achieve 100% code coverage and to really see that your programs work as expected. Let's take a look at something slightly more complex. We saw all synchronous operations until now. Let's take a look at something that is asynchronous. We're going to build a very simple HTTP GET operation using Node HTTPS. This operation might fail for an HTTP error, and then we want to also have a JSON decoding, and we can see that it can fail for a JSON error. As before, service description. This time, we require the operation to be asynchronous. API, as before, simple GET, and then we have a composed API that does GET and then parses the result into a JSON error if there is an error, or otherwise into an unknown response. How do we implement this? We use the asynchronous combinator. The asynchronous combinator takes it takes a lambda, it takes a function that takes a resolve function. The resolve has to be called with an either, can either succeed or fail, and it has to return a canceller, a cancellation function. The cancellation function can be itself asynchronous, so you can do asynchronous cancellation and failable cancellation. The cancel will be called whenever you interrupt the computation, either manually or, as we will see slightly after, if something goes wrong in some types of combinator. I have to rush because I see we have only 5 minutes left. Yeah, basically uses the HTTPS GET. It's a callback-based mechanism. You also have ways of embedding promises and anything else you want. I won't bug into the details, but basically I'm folding all the chunks with a monoid into a single output. And in case it's cancelled, I destroy the request. Live HTTP client. let's take a look at some usage. I'm gonna skip over this part at all. It's based on IOTS. It's for type safe decoding. We have from the result an unknown. In this case, we wanna check if the unknown is a to-do, and we use IOTS to do that. It's very smart, but I won't bug onto the details of this. Another potential errors, our get-to-do function. Our get-to-do function takes an ID, gets from the placeholder JSON API, it decodes the response and embeds the error. Let's run this in a simple example, get a single to-do and show it. It works as expected. Let's take a look at interruption. So as we saw before, this time we run asynchronously. The asynchronous run returns a cancel. If we hit cancel, this request will be canceled. And the exit state is now an interruption. We can sequence a number of operations in parallel. Okay, apparently I've hit the limit from placeholder to-dos. Sometimes they have request throttling, returns properly. If we're not bugged by, well, if we want fast failing operations, so if at the first failure, wherever it happens, everything else is interrupted, we can use the par-fast combination. Fast stands for fast failure. We see that in this case, the fourth operation is gonna fail, and we wanna log that the first one was actually interrupted, just to demonstrate it. And we saw that we had the trigger and the interrupted was actually called. This is very useful if you have large number of things to do and you have an error somewhere. There's no need. If you don't care about the results of the other, there's no need to run everything. It's automatically interrupted. Can do the same, but transversing arrays, and there are many, many combinators that you can all find. They're not hugely documented yet because there's a lot of active development, but they will be. Fundamentally, that's the same type of thing. Again, reach the limit, and everything returns properly. We can use managed resources as in Zio. In this case, we're bracketing over a file. I won't bug into the details of this, but basically we are stitching two resources together, two files together. We're then consuming those and producing the results. File and save. We have the two files, demo A and demo B, properly acquired, released, and combined. Last data type, really to rush. Streams, you can do any streams, computation over streams. Pretty much the same logic. Both managed stream are all 4 parameters. So you can do all the environment things over managed, over streamed, and combine them. And the last part of the demonstration, the most interesting one, we simulate a database. In a database, we want to have a service that accesses the database. The database have a connection that is to be opened and closed. So we build a managed connection, as we saw before. Then we map the managed connection and implement the database in terms of the managed connection. So this is going to be a managed database, and we can use a managed.provide, passing the managed in to return a normal provider. So when we have this type of program that uses the database, we can then have the live program and the environment provided via a managed. And when we do that, the manager will open the resource, provide it. When the program ends or fails for any reason, safely conclude the operation. Just run it for the sake of it, 7.1, and we see that we've got WinBar. I'm running out of time, so I do have to stop. Thanks everybody for joining. It was an extreme pleasure to present at this beautiful conference.